It's Nikos Karampatziakis.
Yeah,
Okay. I'm Paul Mineiro.
All right. Thanks. This is I'm Nikos, and this is John with Paul Mineiro. So I'm going to talk about principal component analysis, which is this method for finding the subspace where the data live. So imagine your data is this point cloud in 2 dimensions. We say we find 2 directions, and we usually project the data on the dominant subspace. So we will find that line here, we will project our data, and this is the best we can do in terms of square depth. So to compute these directions, we can use SVD or eigendecomposition, which I have written here as a sum of random matrices. And you truncate the sum on K to get the best subspace of dimension K. So what are the computations involved in doing this? So we have n examples and p dimensions. And suppose that p is less than n. If it's not, then just transpose it. We can use numerical linear algebra algorithms, and we can get all the eigenvectors. And you go through your data once, construct your covariance matrix, then do your eigendecomposition. That's order p squared, but it's only one pass over your data. If p is large, then you might want to just collect the top k eigenvectors, and that's you will do something like Lanczos. So that requires now k passes over your data, and less work. Then there are these other algorithms that are becoming, we're getting into the randomized zone. So this is proposed about 15 years ago. You just assume you just project your data up front to k dimensions and work with a k by k matrix. So that requires one pass, but accuracy suffers. And then there are these new randomized SVD algorithms, and basically they require a few passes over the data, like 2 or 3, but the accuracy is so much better. And yeah, again, you work with small matrices, like number of maybe dimensions times number of components you want to extract. So how do they work? If suppose we will make the assumption that for now the rank is k, and therefore if the rank is k, we just need to find the k vectors that span the range of the matrix, and then you just extract the argument. So just once you have the basis for that, you just rotate that basis. And to do that, to get to a good basis for the range, you can just start with k random vectors, then feed them to your matrix and orthogonalize their images. And then the nice trick is that once, if the rank is not k, you can just use a small oversampling, like k plus 10 with high probability will give you a good result. So that's the basic idea. An implementation looks exactly like this idea. So you have a random Gaussian matrix, and then you hit your data with this matrix. So you can do that in a streaming, maybe I should say, in an out-of-core fashion. So you can go through and compute this Y matrix, that is P by K. You orthogonalize it. Now you have a basis for the dominant subspace. Now you basically go through the data again, compute the eigendecomposition of Z transpose Z, and basically that gives you the right rotation. So this is in this paper by Halpern. It's a very nice paper. If you haven't read it, you should. The thing is, like, sometimes we have both n being large and the number of features being large. In that case, it's good that these algorithms have a few passes, but there is an orthogonalization step involved. And no matter how we transpose our matrix, orthogonalization is going to be expensive. So these algorithms need this much space and this much time. And the idea here is, like, the problem is, what can we do to, can we sort of like avoid this when both n is large and p is large. So our idea is, suppose that we have a tuning parameter d, and this is something that will allow us to interpolate between one pass upfront random projection and two pass algorithms. So imagine we have a structured random projection that takes our features and maps them into d dimensions. So it can be Hadamard or Fourier or hashing if your data is sparse. And then you choose d according to your hardware or according to whatever budget you have. And so in our experiments we use like a million. So this is the original algorithm, and the modification is very simple. Notice that these matrices here are p by k. The only difference is we multiply with our structured randomness here, 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 and here. Now these matrices are d by k. Nothing else has changed, except that we don't. It's a little bit interesting. So you might wondering why we need both omega here and h. So omega makes sure that this part here is k by k. We didn't have it. This would be d by d. And h makes sure that this part here is small. So by using this intermediate structured random projection, we have reduced the memory requirements, we have reduced the time for orthogonalization, and we have reduced communication costs in distributed implementation. In distributed implementation, we have a poster at the big learning workshop. We send around a matrix that is much smaller. It's a p over d factor smaller. So we tried this on a data set that has 8 million examples, 30 million features. We used a very well-known randomized SVD algorithm, and in particular in a mode that knows that it has to do PCA, so it's not computing the full SVD. It needs 17 gigs of RAM, takes 26 minutes. Our method with a million intermediate random projections in the same setup needs less than a gigabyte. You can like run it on your phone. So it takes a little bit less time. And why would you do PCA? Well, actually, you can just here's some motivation. Like you can just take the top 5 components first with the raw features. You beat the winning submission on this competition. So to sum up, this poster over there describes, in this talk, describes a scaled up randomized SVD that offers reduction in time, memory, and communication. And in the poster we have a theorem, details on distributed implementation, and a cool embedding of 20 million Twitter accounts we did on a laptop. Thank you.